Hello everyone, welcome to part 2 of the video lessons for chapter 10 of the Foundations of Scalable Systems. In this lesson I'm going to start talking about NoSQL databases, which have become a popular alternative to relational databases in the last decade or so. I'm not personally brave enough to try and construct a coherent narrative describing the forces that brought about the creation of a new generation of NoSQL database technologies. My personal inclination is that this innovation was driven by a confluence of reasons that started to gather momentum in the early 2000s. In no particular order, as shown on this slide here, here's some of the reasons. First, the development of powerful low-cost commodity hardware, including multi-core CPUs, faster larger disks, and increased network speeds. Second, the emergence of applications that dealt with unstructured data types and rapidly evolving business and data models. No longer was the one-size-fits-all approach of relational databases applicable to all of these new use cases. Next, the increased need for scalability and availability for internet-facing applications. And finally, new opportunities to gather raw data and utilize this for new business insights and analytics. Combined with the complexities of scaling relational databases for massive data sets, issues I touched on in the previous video lesson, the time was ripe for a new database paradigm. The NoSQL database ecosystem that blossomed to address the evolving business and technological landscape of the early 2000s is by no means a homogeneous place. Several different approaches emerged and were implemented to some or more extents in various, mostly open source databases. In general, however, the core characteristics of the NoSQL movement are listed here on the slide. They have simplified data models with no fixed schemas that can be easily evolved. They have proprietary query languages with limited or no support for joins. Again, this is very database dependent, as we'll see later. They have native support for horizontal scaling on low-cost commodity hardware. Another area of contrast between relational and NoSQL databases is data modeling. Data model normalization, as encouraged by relational databases, provides a proven technique for modeling the problem domain. It creates models with a single entry for every data item, which can be referenced when needed. Updates just need to modify the canonical data reference, and the update is then available to all queries that reference that data item. Due to the power of SQL and joins, you don't have to think too hard about all the weird and wonderful ways the data will be accessed, both immediately and in the future, which of course is extremely hard to predict. Your normalized data model should, in theory at least, support any reasonable queries from the application domain, and SQL is there to make anything you want possible. With NoSQL databases, the emphasis changes from problem domain modeling to modeling the solution domain. Solution domain modeling requires you to think about the common data access patterns the application must support and to devise a data model that supports these accesses. For reading data, this means your data model must pre-join the data you need to service a particular request or query. Essentially, you produce what relational modelers deem a denormalized data model. You're basically trading off flexibility for efficiency. Another way of thinking about solution domain modeling is to create a table per use case. As an example, skiers and snowboarders love to use their apps to list how many days they've visited their favorite mountain each season, how many lifts they've rode, and what the weather was like. If we were designing a schema for a relational database using normalization, you'd probably produce something like this on the slide here as a logical data model and create tables to implement the model. Using SQL, it's easy to then join the data from these tables to produce summary reports such as the one on the slide. This basically generates a list of visits for a specific person for a particular season. This is all very simple with the wonders of relational technology. If you were modeling this scenario for a NoSQL database, you'd probably create a data model that has the results of the query all together in a single table. This is the visits day table as shown on the slide here. This has all the data items needed to generate each line in the list of the report that was on the previous slide. You simply just have to sum the number of visit day objects in the results set to calculate the number of days for a single person. The snow sports person, resource and weather tables would remain unchanged from your original model. This means we've duplicated data across your logical tables. In this example, most of the data in these tables is write once and never changes, such as the weather conditions for a particular day. So duplication just uses more disk space, not really a major problem in modern systems. So there you have it. If you design your data model to efficiently process requests based on major use cases, complex operations like joins just aren't necessary. Add to this, it becomes easier to partition and distribute data, and the benefits start to stack up at scale. The trade-offs are that typically reads are faster and writes are slower due to data duplication. You also have to think carefully about how to implement updates to duplicate data and maintain data integrity. There are four main categories of NoSQL data models as shown on the slide here, namely key value, document, wide column, and graph. They're all somewhat simpler than the relational model, and I'll talk about each on the following. Key value databases are basically a hash map. Each object in the database has a unique key that is used to retrieve data associated with that key. To the database, the data associated with the key is typically opaque. It can be a string, JSON, an image, a video, or whatever else the business problem demands. Examples of key value databases include Redis and Oracle NoSQL. A document database builds logically on the key value model, again with each document in the database requiring a unique key. The value associated with the key is not opaque to the database, rather it's encoded typically in JSON, making it possible to reference individual elements in the document in queries, and for the database to build indexes on individual document fields. Documents are usually organized into logical collections analogous to relational tables, but there's no requirement for all the documents in the collections to have the same format. Leading document databases are MongoDB and Couchbase. A wide column database extends the key value model by organizing data associated with a key in named columns. It's essentially a two-dimensional hash map, enabling columns within a row to be uniquely identified and sorted using the column name. Like a document database, each row in the collection can have different columns. There's no need for everything to have the same format, the same schema. Apache Cassandra and Google Bigtable are examples of wide column databases. Graphs are well understood data structures for storing and querying highly connected data. Think of your friends on Facebook, or routes flown by airlines between airports. Graphs treat relationships between database objects as first-class citizens, and hence enable a wide range of graph-based algorithms to be efficiently implemented. Conceptually closest to relational databases, prominent examples are Neo4j and Amazon Neptune. NoSQL database query languages are nearly always proprietary to a specific database. They vary between explicit API capabilities and SQL-like declarative languages. Client libraries in various languages implemented by vendors as well as third parties are available for utilization in applications. For example, MongoDB officially supports 12 client libraries for different languages and has third-party offerings for many more. Key value databases typically offer little more than APIs that support CRUD, create, read, update, delete operations based on individual key values. Document databases are normally a little bit more powerful, supporting indexing of individual document fields. This enables efficient implementations of queries that retrieve result sets and apply updates to documents that satisfy various search criteria. For example, on the slide here is a very simple MongoDB query that retrieves all documents for skiers from the skiers database collection and only retrieves individuals who are older than 16 and have not renewed their ski pass. In contrast, graph databases support much richer query capabilities. OrientDB, a leading graph database, uses SQL as the basic query language and implements extensions to support graph-based queries. Another very widely used example is Cypher, originally designed for the Neo4j database and open sourced through the Open Cypher project. Cypher provides capabilities to match patterns of nodes and relationships in the graph and powerful query and insert statements analogous to SQL. The example on the slide here returns the emails of everyone who has visited the resorts node with the name property of Mission Ridge. NoSQL databases are a key part of the infrastructure for building scalable systems, and this video lesson has covered the very basic features and capabilities you'd expect to find in a NoSQL database technology. Next, I'm going to move on to talk about data distribution strategies, which are absolutely necessary to build scalable database platforms.